introduction of our solar system, and the presenter is Driss Takir.
All right, thank you very much, Hannah. Well, first, can you hear me okay, everyone?
Yes.
Yes.
Excellent. Yeah, well, good morning, everyone, everywhere. Thank you, Hannah, Amanda, and Survey for organizing this virtual meeting that bring modelers, cosmochemists, astronomers together to discuss one of the most outstanding topics in planetary science. So here I'll be discussing with you some of the work that we've done on carbonaceous chondrites and carbonaceous asteroids. Just to mention, after I submitted this abstract to the workshop, I joined the Materials group at NASA JSC in Houston, Texas. Okay, let's see if I can remember how to drive this. Is there a way to go forward?
Hi, Driss. There should be an up and down arrow at the bottom left corner of the slides.
Oh, yeah, that's right. Thank you very much, Ashwin. Yeah. So this is the outline of my talk. So I will cover four main topics. One was nicely covered by previous speakers, by Hannah and others. So we'll discuss carbonaceous meteorites. And here I'm going to focus on chemical compounds, mainly organics, and carbon-rich minerals. Also, I will talk to you about some of the ground-based observations that we've been doing and conducting on carbonaceous asteroids. Again, I'll be focusing on chemical compounds, organics, and carbon-rich minerals. And number three, I will discuss with you the attempt of linking the results from lab experiments on carbonaceous chondrites and astronomical observations of carbonaceous asteroids. And then finally, I will talk about conclusions and future directions and discuss some of the outstanding questions and works that needs to be done next 5-10 years in order to for us as a planetary scientists to advance this field and also to be able to address the outstanding questions in planetary science, for example, carbon in the solar system. All right, next. All right, so as you know, from Astronomy 101, the current inventory of elements in the universe were generated by several complex processes. Helium and hydrogen, lithium were created in the Big Bang phase in advance about 14 to 15 billion years ago. Then first stars were formed and galaxies, and heavier elements than hydrogen and helium, including carbon, were produced and generated in stars by processes like stellar nucleosynthesis. So for astronomers, to note, for astronomers, there denote three elements: so hydrogen and helium, and everything else is classified for them as a metal. So here I'm not including planetary astronomers. I'm here talking about astrophysicists. So, but one of the most important reactions that involve carbon in stars, especially AGV stars, is the triple alpha process, which involves three alpha particles or helium to generate heavier elements like carbon. And then carbon, nitrogen, oxygen cycle, where fusion reactions took place to generate even heavier elements like magnesium, like neon, and then carbon burning, where carbon is reacting with each other to produce heavier elements in nuclear infusion reactions. So on the right, I'm showing an illustration of a red giant star that shows onion shell structure with helium and hydrogen on the top and heavier elements on in the bottom, in the core of the star. Now, the red star, as you know, emerged or become a supernovae, and from the recycled elements from the explosion of the supernovae, nebula or solar nebula was formed, including our solar system. So here I'm showing an illustration by Bill Hartman. This is a painting, a nice piece of work and art done by Bill Hartman at the Planetary Sciences Institute, and it shows a conception of the solar nebula surrounding the violent young star. So in my talk, I will focus on meteorites and asteroids. Why? Because they offer a unique window of the solar nebula that allow us to go back 4.5 billion years ago and study the origin and the evolution of the elements that were formed during the beginning of our universe. So just a reminder, 86% of meteorites that we have in the lab are chondrites, meaning includes chondrules. And in my talk, I will mainly focus on carbonaceous chondrites, CIs, CNs, CRs, CVs, COs, and CKs. And these are thought to be primitive meteorites. They were formed under low temperature, and they were also aqueously altered. They were not thermally metamorphosed like ordinary and ancestite chondrites. So far, we've found about 300 different mineral species in meteorites, and 78 different, 78 minerals of these minerals are hydrated minerals. 15 about, let me use my, yeah. Oops. Yeah, so 15 minerals are considered carbonates or carbon-rich minerals, and this is a nice table that I borrowed from Mike Lansky, and I updated it with some of the newer data, with some data that were published in a review, the book by Burley and others, and I'm highlighting the carbon-rich minerals. So here I'm showing all the CNs or carbonaceous chondrites, including CIs, Ivona-like, CNs, and Ega-like, CO, CV, CV, CH, CR, and Tagish-like. So I'm highlighting the carbon-rich minerals, including calcite, dolomite, aragonite. And I will cover some of these minerals in my talk. We've done, Hannah pointed out earlier in her talk, we've done some lab work under vacuum and then elevated temperatures to simulate asteroid-like conditions on carbonaceous chondrites. And here's a summary of our work from 2013 that shows reflectance spectra of carbonaceous chondrites that were measured again under asteroid-like conditions. Some of them exhibit carbonates, like for example, MAC 0260606, and also Iona. However, we're still not sure if those carbonates are due to terrestrial contaminations or due to extraterrestrial material. So especially for MAC, because it's an Antarctic sample, and it's been sitting in Antarctica for millions of years before they were collected. But as we heard earlier, we have to work with what we have. So again, carbonates exhibit a strong CO2 absorption, and especially in the 3.4 and 3.5 micron, and also at 3.8 and 4.8 microns. As you heard earlier, these features, overlap with aliphatic organics features around 3.4 and 3.5 micron. Now I'm showing a Raman spectra that we measured for MAG 06606, because dolomite has magnesium, and reflectance spectroscopy is not sensitive to magnesium. However, with Raman, you can differentiate between dolomite, which has magnesium, and calcite, which doesn't have magnesium. Yes.
Driss, sorry to interrupt you, but we kind of need to keep an eye on the time, and you've got about a couple minutes left in your talk window.
Oh, okay.
So,
right.
Might want to move along.
No, okay. So I'll go fast. So, so these are more data that we've collected just recently, and one of people that I work with from the Haihuza to Izokoi, Haihuza to were able to measure more carbonaceous chondrites, including CRs and CVs. And one of the interesting things in this work is CIs have a tendency to absorb more volatiles and also organics. So here we one of APL interns, he's now a graduate student at the University of Hawaii, Genesis Baranga, did some experiments CO2 gas absorption, and we found out that CIs have tendency to absorb more volatiles and also organics. And we explained, or Genesis explained that, or interpreted that as or by the fact that CIs have abundant clays and oxyhydroxides. All right, so again, this some of the experiments that we've done, and again, we found, as Hannah showed earlier, the organic features become more pronounced when absorbed water is removed, and the best explanation for for this is that absorbed water mask organic features. Now moving on to asteroids. So it's we've been focusing on primitive asteroids and trying to link the spectra that we've been measuring using telescopic observations. I'm trying to link it to meteorites and trying to understand the morphology of these primitive carbonaceous chondrites. And here are some of the matches, we found that polysilicate rich asteroid match best CM carbonaceous chondrites. No matches for other asteroid spectra, for example, Ceres, and spectra that been interpreted as water-rich spectra. For example, Themis, Hannah showed earlier, 24 Themis by Rifkin and Emery. Also, so far we've detected organics on asteroids, and it's been covered again by the previous speakers. So here's my conclusions, and my apologies for going so fast. Again, my conclusion, so I made this slide last night and came up with the C diagrams, and for carbon, just for fun. So laboratory experiments are very important, like the great work that, for example, Hannah is doing, Brown and others, is very important. Also, it's very important to try to link lab work to ground-based observation and spacecraft data from asteroids. So we have two spacecrafts on their way to Carbonaceous chondrites, which is going to bring a sample back to us in 5 years. So we'll have an opportunity, to discuss, to analyze that. Now, the other challenging thing that needs to be done in order to address some of the outstanding questions in planetary science in general is to try to tie what we learn in our lab and also from surveys, asteroid surveys, for example, try to tie it to other astrophysics disciplines. For example, study of accretion, there's using models and also using observation. And with that, I will conclude my talk. Thank you very much.
Great. Do you have any quick questions? Nothing? I think maybe we'll take this opportunity to move forward since we're going to run behind schedule a little bit. So